Dropped object problem. Sample problem 2. A student drops a rock off the top of a tall building. The student notices that the rock hits the ground 2.6 seconds later. How tall is the building? So you draw a sketch just so you can make sure you know what's going on, and this is violating all kinds of OSHA requirements. Students should not be this close to the edge, should be a safety harness here. And why is the student dropping a rock off a building anyway? Well, let's just do the physics problem. The initial position is unknown, right? We're trying to find out how tall the building is. That's another way of saying what is the initial position of the student. So x sub 0 is equal to question mark, and we found that through the sketch. The rock lands on the ground. Our final position, the ground we typically take is x equals 0. We also see the rock moving through the air, so we can use a as minus 9.8 meters per second squared. And the minus sign, why is that? Well, because it's going in the downward direction. Now we list our variables and any appropriate constants, and the variable looking for. So from our sketch, we have our initial position, x0 is question mark. That's what we're trying to find. Here's our final position on the ground, x is 0, and here's a constant. A is minus 9.8 meters per second squared. So actually, what is a equal to? It's equal to minus g. G, by the way, is always a positive 9.8 meters per second squared. The negative comes in when you're using it as an acceleration and it's pointed down. What else do we have? We have time, 2.6 seconds, and since the rock is dropped, its initial velocity is 0. Now we put all our variables and what we're looking for and constant right here so we can look at them together. What equation do we want? We've only got 3. We're going to use the second kinematics equation. Why? Because we have x, we have x0. Well, actually, no, we don't have it, but we're looking to find it. Sorry about that. We have v0, we have time, and we also have the acceleration. So we have everything except x0 in this equation, so we're good. There's no mention of the final velocity in this problem. We could have asked for it, but we didn't for this particular problem. Once again, we have our variables, constant, and what we want to find up here. Here's our equation, second kinematics. Now, what equals 0? X is equal to 0, so we replace it with the 0. V0 is equal to 0, so this term just goes out, and we're left with 0 is equal to x0 plus 1/2 at squared. Make sure you leave that 0 on the left side for x. What do we have to do now? We'd like to get x0 all by itself. So let's subtract from both sides 1/2 at squared. And let me just erase this box so I can illustrate that. Here we go. Subtract 1/2 at squared from both sides. And what happens to the right side? Well, it goes out. We're just left with x0. But we added a negative 1/2 at squared on the left side, or subtracted 1/2 at squared, however you want to say it. We're solving for x0, so we're going to switch the equation around. It's just like saying, let's see, 1 plus 1 equals 2. Well, you can switch that to be 2 equals 1 plus 1. So we just do that here with the letters. So here's the equation. Notice we haven't plugged anything in yet, no numerical values. We could have done this for any acceleration, any time. Finally, we're ready to put the numbers in. So we have minus 1/2 times negative 9.8 meters per second squared because it's accelerating down. And here's our time. And one of the most common mistakes on this particular problem is forgetting to square the time. So please square the time. And what's cool here is the negatives will cancel out, so we'll be left with a positive height. Now, as you go on in physics or science, there's something called significant figures. That means if your givens have like 12, you have 12 times 12 or something like that, you cannot have, well, that's actually a bad example. So let's take 10 divided by 3. 10 divided by 3 is 3.333333, etc. You really can't measure that precisely with an infinite amount of 3's after the decimal point. So there's a lot of talk about significant figures as you go through science. We're not going to worry about it here. We just want you to learn the physics. So we're going to make a rule. Whenever we have an answer, we are going to round it to have just 3 digits. We don't care about the decimal places, just 3 digits. So here we have what? That's 5 digits. We want 3, so we're going to round that to 33.1 meters. Okay, this way we'll just keep it simple. We won't worry about significant figures yet. And now the advantage, just to advertise, why did we solve the equation first without putting numbers in earlier? Let's say the student now goes to another high place and drops something and finds the time, and he wants to, or he measures the time and he wants to know how high up he was. He just goes right to this equation and just plugs in a different value for t. He doesn't have to do all the work again.